All right, here is day 4 lesson in differential equations. This is on Euler's method, and Euler is pronounced like the word Euler, not Euler. And what we're going to do now is kind of expand on what we did, introduced briefly on day 1 when we looked at the water coming out of the barrel. On that day, we came up with a very rough numerical solution to a differential equation. And we told you that we would get into Euler's method today to get a more particular solution or a more refined solution, still numerically. So in this case, we're going to start with this function dy dx, or this differential equation, dy dx equals y, with the initial condition of the point 0, 1. First method we talked about was graphical method, or slope fields. So since the derivative, or rate, is equal to the y value, come over to the slope field, and everywhere where you have a y value, say, of 1, you have a slope of 1. Then when your y value is 2, you have a slope of 2, and I'm doing my best to make these slightly more steep than the slope at 1. Slope at 3 would be more steep even than that. It would have a slope of 3. And I could keep going and doing my best to make these look even more steep. The higher the y value, the steeper the slope is going to be. Then I could come back down here to where y equals 0, and if y equals 0, then dy dx equals 0. Then to find the solution at the point 0, 1, I just go over to the point 0, 1 and then sketch a solution curve that follows my tangent lines from my slope field. And there is my solution curve. Second way of doing this is through separation of variables. And what we'll do here is we'll start with dy dx equals y. We'll separate variables by dividing by y and multiplying by dx. Then we will integrate both sides. So we're following separate, integrate, solve. We integrate dy over y to the ln of the absolute value of y equals, this is really 1 right here, and it integrates to x, and we'll put our plus c on the right. In order to solve for y, we need to exponentiate with the base of e. These cancel because we're composing inverses. We'll be left with the absolute value of y equals e to the x plus c, which is the same thing as e to the c times e to the x. Then I will go ahead and condense e to the c into an a value, which is a constant that will allow me to absorb my absolute value. So I have y equals a e to the x. Now I can plug in my initial value of the point 0, 1, and if y equals 1 and x equals 0, then my a value is 1. And my solution becomes y equals e to the x, which makes sense because that's what this curve looks like it is. So that is a graphical solution that gives us just a slope field, and then we can draw a solution through the slope field. We used algebra or separate, integrate, solve to find the actual solution. And then we have also the numerical method, and this was created by Leonhard Euler, who is an 18th century Swiss mathematician. And here's the concept. He said, okay, if the slope field is like these signposts telling us how to draw the graph, then what we could actually do is say at this initial value of 0, 1, we can calculate a slope, and we could draw a little tangent line and take a small step over to the right. And then at that new point, we can calculate a new slope, create a new tangent line, and use that tangent line to step a little bit more to the right. And we're going to create a series of tangent lines, which takes us on a numerical approximation of the actual solution curve. So let's do exactly that. We have a table here for you that you can actually use on the AP exam to justify your work. You will have to memorize what the columns of the table are. They will not provide the table to you, but it's not too much work to do that. We start with our initial value of the point 0, 1. That goes right here. Then we take that point and we plug it into the differential equation to find the slope, which slope is just equal to the y value, so the slope is 1. Tangent line, we put in point slope form. We have the slope, x minus the x value plus the y value. Then x plus delta x, we take our original x and we add to it our step size, which is delta x. So the new x is 0.1. The new y value we get from plugging 0.1 into the tangent line. So we have 1 times 0.1, which is 0.1, plus 1, so we get 1.1. We're then going to take this new point and start our second row with it. So this is our point p sub 1. The slope is equal to the y value, so here's our slope. The point slope form of a line is the slope x minus the x value plus the y value, using the x and y value from this point p sub 1. The new x value will be the old x value plus another step size of 0.1. We're then going to plug 0.2 into this tangent line equation. We get 1.1 times 0.1, which will get us 0.11. Add that to 1.1, and we get 1.21. Take this point, bring it over as our p sub 2. Then, since our y value is equal to our slope, the slope is 1.21. New tangent line equation, y equals 1.21, x minus 0.2 plus 1.21. New x value is 0.3, plug in 0.3 here, and you will get out 1.4641. And I can continue on. My new point will be 0.3, 1.4641, slope 1.4641. Write in a tangent line equation, you'll get your new x value of 0.4. Then this will give you 1.61051. What's interesting about this is that these first few rows, and as I'm looking, I found a mistake, so I'm going to erase and drive you guys crazy that I put down the wrong value. Sorry about that, my math brain failed me. This is 1.331. That comes down here to 1.331. That is my slope. My new tangent line is 1.331. X minus 0.3 plus 1.331. My new x value is 0.4. My new y value is 1.4641. Sorry about that. Notice how these y values, for those of you that know what Pascal's triangle is, notice that these are the second, third, fourth, and fifth line of Pascal's triangle, which comes from counting theory or combinations and permutations, which is kind of interesting that that is a connection here. So basically what we're doing is we are approximating these y values on the curve by using these small steps and coming back up to the graph. We're starting here, we're moving a little bit, doing a different color, a little bit to the right, a little bit more to the right, a little bit more to the right. And we're approximating the values on the actual solution. So, how accurate is this? Well, first of all, what you should know is this table of values is just brought from the prior page. These are the approximated y values. We can't get a function out of this, but this table itself is a function. We just can't get an equation out of this. But these are approximate y values using this increment of 0.1 and a starting value of 0.1. So this is our Euler's approximation of the solution to this differential equation. These are the exact values of y equals e to the x. What you'll see is that at the point 0,1, the two curves are equal at the starting point, which makes sense. Beyond that, though, things start to change. This is 1.1, this is 1.105, etc. Looking at the graph, you'll see this nice smooth solution curve. This is the actual curve of y equals e to the x. These are incremental tangent lines using Euler's approximation. So why would it be that Euler's approximation underestimates the actual solution curve? Well, it's because y equals e to the x is concave up. And this takes you way back to Unit 1 of this course when we showed you that in a concave up function, the tangent line will underestimate the curve. All these are tangent line approximations, and so the linear approximations will underestimate the curve, and what ends up happening is that e to the x is going to grow exponentially, whereas these linear functions will not, so the disparity between the solution curve and the Euler's approximation will increase, increase, and increase. So that means the approximations are getting worse, and you can tell that in this table, which shows you the difference between the actual y value and the approximation. There is no difference at the initial value. And then as you increment by 0.1 on the x-axis each time, do you see how the difference in y values is increasing and increasing? And it's actually increasing by a lot more each time. So what can we do to make a better Euler's solution curve? Well, we can decrease the step size. And that means use a smaller delta x. So in this case, maybe we'd want a delta x of 0.05 or even 0.01.